Hi, welcome to our third webinar in this series for Balanced Assessment Systems for Science Education. Today we're going to talk about connecting curriculum to instruction and assessments for science. If you have participated in some of our previous webinars on this subject, then some of the things that we're going to talk about may be repetitive, but many of the things that we're going to talk about really do fit into how we connect curriculum, instruction, and assessment across the board. So it's really important that we revisit some of these things. We're going to start with talking about what the goals for assessment really are. And when we talk about goals for assessment, we often talk about having something that is an educational assessment that's intended to support or refute a specific claim. So we make a hypothesis and say that we have students who are overwhelmingly or satisfactorily proficient in the use and understanding of specific standards, in this case, science standards. And if we collect information using an aligned assessment to the standards, then teachers, administrators, parents, and the students themselves have evidence and information that illustrate for them that they have met their goal, that indeed students are able to use the knowledge and practices that they have learned over a period of time to solve unique problems, to do the things that that they were taught to do, and so they know that they have met their goals, and they're ready to carry forward and move on. At the same time, if results indicate that students have not met the goal of proficiency, so they haven't gotten to the point where they're able to use their practices and their content, their cross-cutting concepts regularly, in illustrating their understanding of specific standards, then teachers, administrators, parents, and again, those students have specific evidence and information that they can use to figure out what it is that they need to do in order to remediate or change what's happening so that they can do better as they move forward through ongoing instruction. So sometimes these goals that we're focused on, they can be immediate. These are things that happen in the classroom: informal questioning, question-answer sessions, modeling activities with productive talk, performance tasks, those sorts of things. They may also, however, be focused on specific and identified breaks in instruction, where teachers are measuring summative zones of understanding. So you may have had a unit of instruction and students are trying to illustrate their understanding of what you've taught, and teachers are measuring and gathering evidence as to whether or not students are able to illustrate independently their ability to achieve the goals that were set forth in that previous unit of instruction. At the same time, sometimes an organization or a system is measuring a hypothesis that that system or organization is meeting the needs of the students that are within its boundaries. And under that setting, then a state or a federal summative assessment is intended to gather evidence that students have met the standards. In general, those are given in specific gateway years, and for science, that's in grade 5, grade 8, and high school biology. And in all of those instances, whether it's a classroom formative assessment, a benchmark assessment, or a state summative assessment, we want to make sure that the curriculum, the instruction, and the assessments are all aligned. They're all in alignment with one another and in alignment with the goals that we have for our students, so that we know that everything that we're doing is intertwined, and that the goals for curriculum, the goals for instruction, and the goals for assessment meet together for the student, and that we aren't measuring inconsistently what it is that we're doing in the classroom. And this model or illustration really kind of talks about that in a very generalized way. We have investments that we place in the classroom and we put forward for our students. We invest time for curriculum and materials. We invest time and effort for professional learning. And of course, we invest time and effort for instruction. And all of those things are invested in our students. And then we measure to see how well those things have worked by giving assessments to our students to see how well they've learned or retained the information that we've given them. And we know, we are all very well aware that there are many other variables that affect our students on a day-to-day basis than just the curriculum, professional learning, and instruction that is provided for them. But one of the things that we are working with is the information that we provide for our students and whether or not they're able to retain that. So if we use assessment correctly, then the data that we receive from those assessments can assist teachers and administrators in making wise decisions for the improvement of student learning over time. Classroom formative assessment data can be used immediately to inform what's happening on a day-to-day basis in the classroom. Benchmark assessments can provide data that can help us decide what we're going to do moving forward. So is there something that we need to build into our ongoing curriculum and instruction to help support our students? And then at the higher level for state assessment, we can look to see, are there trends in the data, are there patterns in the data that illustrate that there might be something that we need to do at the organizational or systemic level to assist our students and our teachers in meeting the goals that we have set. So again, aligning the assessments with instruction and of course professional development and curriculum, it's all imperative. And one of the ways that we do that is, of course, to teach to the standards. It doesn't mean that we can't teach extra things or to teach information that helps support the standards in innovative and different ways. But one of the things that we really want to do is make sure that we are teaching the information, the practices, and the cross-cutting concepts that are actually in the standards. And so to do that, we want to make sure that we have a clear understanding of what the standards are, what's expected by the standards, how to read them, and how to use them as we build our lessons and our curriculum and our instructional processes around them. So if we click on this link, then it'll bring us to a page that looks like this. How to read the next generation science standards. This page actually has a short webinar of its own. It's only about 6 minutes. That if you push play, it actually takes you through how to read the next generation science standards. So you'll see that in this section, it talks about the 3 dimensions of science, the practices, the disciplinary core ideas, and the cross-cutting concepts. It explains how each of these things work in the next generation science standards. It describes how they are built to create the structure of the standards, how each performance expectation or standard itself is written so that each of the 3 dimensions are built into each of the statements, the organization of the standards themselves, the 4 domains of the standards: physical science, life science, earth and space science, and of course engineering, technology, and applications of science. It talks about the disciplinary core ideas or the content, how performance expectations are labeled, and it also talks about the performance expectations and the layout of the document itself. So when you come in, each of the performance expectations are listed at the top of the page, and then three dimensions are listed in colored boxes at the bottom of the page. So if for any reason someone in your district or you yourself have had limited experience with reading the next generation science standards, then it's recommended that you come to this site and spend a short 7 minutes watching this video. It'll explain that to you, and then you can actually take some time to investigate and play around in the next generation science standards website. The standards are actually available not only online, but also as a printed PDF, or you can order them online. You can even order them from Amazon.com or from NSTA.org. NSTA is the National Science Teachers Association, for a printed version. So these are available in multiple document types, digital and printed, and it's highly recommended that you take these short 7 minutes to get acquainted with them so that you're exceptionally comfortable with how they're written, what the expectations are, and how to use these standards in action. The next thing to take a look at are these shifts between the old and new standards. So if you click on the link for the shifts, you'll come to this page, which illustrates the shifts between older standards and newer standards. I will say, in the state of Delaware, with the past 20 years' focus on inquiry-based approaches to science, these left-hand foci of rote memorization of facts and terminology and teachers providing information to the whole class, there should have been less of a focus on some of those things in the first place. But on this right-hand side is what we're really looking for in next generation science standards. And we want to make sure that what we're seeing in classrooms are students learning facts and terminology as they're developing explanations and designing solutions through evidence-based arguments and reasoning as they're looking at and investigating phenomena or scientific observations. We want to see students building models and revising their models in science. Building and revising models doesn't mean drawing pictures and drawing labels. It means illustrating something and using a model to explain something scientific. And then having other peers, whether it be students or teachers or a combination of both, provide input for how those models might be modified to make them more robust. And then using other sources and resources, just as you would in ELA, to collect further evidence and information to help revise those models and make them, again, more robust and explanatory. So models should always be something that can be revised over time with multiple sources and inputs. We want to see students discussing their questions and ideas. We want to see them reading multiple sources and resources. We want to see them writing and revising their writing over time. We want to see a lot of discussion and a lot of thinking that goes into building ideas and changing their ideas over time so that students are building their understanding from a previous conception to a new conception and a more mature conception over time of scientific ideas. So this is what we want to see in next generation science standards, what's on the right hand side, and much less of this idea of memorizing terminology and taking notes from teachers and memorizing ideas of information that's been previously investigated and known to be true. We want them to take that information that's already been investigated and known to be true to build on their own understandings and building new models and new understandings as much as they possibly can. To assist with this idea, some of the things that we want to see in curriculum and instructional processes are some innovations that are recommended by the National Academies of Sciences in a document titled A Framework for K-12 Science Education. These 5 specific innovations or expectations are things that are required and shared by the academies to help ensure that a curriculum is considered aligned with the expectations of the next generation science standards. And they include things like making sense of phenomena or scientific observations and designing solutions to problems in an attempt to help drive student learning. To have three-dimensional learning, where students are using the practices, cross-cutting concepts, and disciplinary core ideas to help engage them in making sense of the scientific observations that they're engaged with, to require students to actually perform some sorts of tasks. These should be grade appropriate, and we want to make sure that students are using practices and content to help them make connections between the things that they're seeing as they're working through different phenomena. We also want to see a progressional building of ideas from kindergarten through 12th grade. So it's not a matter of building new information every year. It's more a matter of building a maturity and depth of understanding from year to year. So students have three-dimensional knowledge and understanding that begins in kindergarten, first, second, and third grade. And as they grow and mature in their abilities and understanding and their practices and their mathematical skills, and their writing and research skills, then they'll be able to have a deeper and more robust understanding of some of the concepts that they have early conceptions of in early grades, and really be able to get deeply into the concepts and ideas as they get further into upper level grades. So students generally will have some ideas of some quote unquote physics concepts of force and energy when they're in early grade school. But then by the time they're in high school, they'll be working through some higher level physics, if you will. But the ideas and the basic foundations of those ideas are the same. It's just that the tools that they use to investigate those ideas become more robust, and the rigor enhances over the years. So we want to see that building of progression from kindergarten through 12th grade. We also want to see an alignment with ELA and mathematics. So just like I was saying, students are going to be using their language arts skills of citation and research and the ability to build an argument from evidence, and to be able to cite concepts and ideas that they're able to find in research materials in order to help them in their scientific investigations. We also need them to be able to use their mathematics skills in order to build data, evidence from data and trends and ideas, and to be able to use ideas that build from mathematic conceptions over time, and to use these things in connection with what they're learning in science. So it's really important that there's an alignment between what they're doing in science and what they're doing in ELA and mathematics through the years. And we also want to make sure that it's very clear and understood that these are standards for all students, that these next generation science standards aren't for some students who are capable, but for all students who are all encompassing and all experiencing the next generation science standards as a foundation for readiness for college and career as they go through their K-12 experiences. So as we understand that we have assessments that build out claims and gather evidence for us, and that we need to make sure that we're teaching and instructing toward the standards that build that core of goal building for us, so that our assessments and our instruction are aligned to a common goal, we need to also think about how that assessment data is tied to our curriculum and instruction. So once we give the assessment and we have the data, how do we tie that information to our curriculum and our instruction? So we know that classroom assessment is immediate. We provide students with questions, they provide us with immediate feedback. And we know that in the next generation science classroom, we're asking teachers to basically be modeling next generation science practices through the process of gathering information from their students, interpreting what their information and data is telling them, and then communicating or acting upon that information immediately to create some sort of change in student behaviors and understandings, which is next generation science in a nutshell: gathering, interpreting, and acting. And so formative assessment in the next generation science classroom is really the embodiment of next generation science practice with students and for students toward the goal of enhancing the learning process for them. So there can be a formal rubric in what you're doing in the classroom, but often this process is kind of iterative. Teachers sometimes make these things up on the fly with a general goal in mind, but it's focused on productive talk, discussion, and argument in a safe environment where teachers and students are working toward developing ever more complex understanding and the use of in the use of scientific knowledge and practice across those domains of science. And as teachers listen and watch students for clues about their current understanding, instant adaptation of instructional procedures can be made to account for those misunderstandings. Or advanced knowledge even, if students are ready to move ahead more quickly. So it is important that formative assessment be inclusive, and that students are sharing information and feel comfortable sharing information with their peers and their teachers as they build those new understandings. Some ideas include things like large circle group conversations that allow for open communication and sharing. And then, of course, those smaller group interactions that allow students to have shoulder partners, or modeling groups that allows for communication for revisions of models and sharing of information among smaller groups. So there's a lot of open communication across the room, but it's important that students feel safe in being wrong. Wrong might not be the right word. Feel safe in feeling like they're ready to revise their thinking. These ideas of things like circle time are really focused on limiting the numbers of distractions for students. And in other words, building a circle so that students don't have cell phones, computers, one-to-one devices, knickknacks, notebooks, pens, pencils in their hands, and that there's just an open communication and discussion time, with the teacher being in the side of the circle and students being able to have open communication across the circle. And these kinds of things allow students to share and clarify their thinking, to actually focus and listen to one another, to deepen their reasoning and thinking, and to share those ideas before they move forward with revising their ideas for further work in the classroom. So again, all of this has to do with classroom assessment and focused productive talk, all of which is meant to allow the teacher to facilitate on-the-ground adaptation of instruction to meet the needs of their students in real time. At the same time, some more formal instructional assessment processes occur with things like end of unit instruction. And we're going to get into something here that you've seen some of this before, but we're going to get into how to more deeply investigate some of the data and the research, and how to apply that to what you're doing in the classroom, and how to maybe apply it to a professional learning community to move things forward in your classroom or in your buildings. So at the end of a unit of instruction, a summative assessment might be something that you give in order for students to share their knowledge of what they've learned during that unit of instruction. Evidence might be collected through an assessment that's provided for you in Performance Plus. There are approximately 14 of those available now. We'll have a full suite of 21 of them by Christmas of next year. And having students complete those assessments so that you can gather information about trends and ideas of their understanding would be helpful in allowing for you as a teacher to identify indicators for different strategies for further instruction and modifying lessons and activities that might be helpful as you move forward throughout the year. Data analysis worksheets are actually available in Performance Plus with these assessments, and if you input the data with these, then you get an output meter that looks similar to this. So once you've put in your data, then the analysis worksheet will allow you to see something similar to this that lets you see that, you know, student with question 1A generally got almost all of them right, but you can see with question number 2, someone didn't get all of the questions correct, or not someone, but in the population, there seemed to be more of an issue here. And also with question 9A, there seemed to be more of an issue, but question 7 seemed to be doing pretty well. The value in this initial analysis is that you can just generally look and see visually which items seem to give students the most difficulty and which ones gave them the least difficulty. As a teacher, I would look to this report and quickly identify column 2 and column 3 as possible targets for investigation because it looks like quite a few students struggled with these 2 items. At the same time, item 1A and B look like they were quite easy for most of the students in the population that took the assessment, so I wouldn't worry too much about whether or not students understood those concepts in the overarching population that took the assessment. But that said, there's more to look at here than simply whether or not the students got the items right or wrong. We can click on something called the report card, which is off to the right hand side here, and we can get more information that looks like this. You can see across the top how many students got each of the items correct. So you can see 33 students got question 1A and B correct, 21 got question 2 correct, 17 got question 3, and so on and so forth. This gives you a very quick opportunity to highlight items 2 and 3 as curious because you can see 21 and 17 students got these correct, so that's quite a few less than question 1. We can also look at question 8B and 9A and B right here and see that not as many students got these items correct either. Further review would allow us to look at individual distractor analysis, so that's looking down here, and see what answer students are choosing instead of the correct answer. And we can look to see, are there misconceptions showing up? Are students guessing in general? And if they're just guessing, in other words, if equal numbers of kids are choosing all of these responses, then that indicates they're guessing, and so that probably means they don't know what the answer is at all. So we can look at a few things here. With item number 3, question number 3 right here, we can see that the keyed responses should be C and E, but 32% of students were drawn to letter B. So there's something about letter B that is enticing to a large population of our students. We might want to look at what that is. With question number 2, the correct response is B, right here. The correct response is B. 57% of students chose B, but 30% of students chose A, so there might be something enticing about letter A, and we might want to take a look at what that is as well. And then when we come to items 9A and 9B, the correct response for 9A is C, and for 9B is D. A majority chose the correct answers. But we do notice that 23% of students chose letter A for 9A, and 26% of students chose letter C for 9B. So again, these are attractive distractors, and we might want to just take a look at those items and see what's drawing students to those responses and whether or not there's something we want to think about reteaching or revisiting with students, or just know as a teacher as we move forward, just to see if there's something we want to adjust in our classroom. So this is just another way of writing what was just said, but we are also focusing in on the standards. So here are the standards that are aligned to each one of those questions. So we notice that 9A and 9B are aligned to this 5PS1-2. Measure and graph quantities to provide evidence that regardless of the type of change that occurs when heating, cooling, or mixing substances, the total weight is conserved. So conservation of mass. We notice that students did fairly well on two of the three questions that were asked. So it might just be this particular item and the way that it was asked that students seem to have an issue. So we might want to look at that. But then again, we might just want to see whether or not they're having an issue with conservation of mass. So we'll take a look at that. With these two questions, question 2 and 3, we notice that there are only 1, 2, 3, 4, there are 5 questions. Students missed 2 out of 5, or a large number of students missed 2 out of 5. So that's significant. And we notice that the standard is that they're supposed to conduct an investigation to determine whether the mixing of 2 or more substances results in a new substance. So this has to do with chemical reactions. So we might want to double check and see what the specific issue is here, but also remember what we did in the classroom that had to do with chemical reactions and think about whether or not there was an alignment with that and the assessment itself, whether or not we were able to actually get to the chemical reactions section of our teaching, whether or not that was something that my students actually had difficulty with, and I remember that. So there are many things that we can think about here. And then we noticed that question 8B was a focus, and we noticed that was carrying out fair tests. So maybe that has to do something with the specificity of having students actually practicing this process of carrying out fair tests and developing their own assessments and research projects. So let's take a look at a couple of the items themselves. I'll just give you a second to look over this. So we see here that the question is asking students which test provides evidence that mixing a powder and a liquid caused a new substance to form. And students are generally, more of them are choosing the correct answer, which is B, the vinegar test, because mixing vinegar with powder caused a gas to form. Okay. So, but some students chose A, the water test, because water caused powder C to change into a soft solid. Okay. Now, this doesn't give you as much of the information for the entire cluster, but students did know that this mystery powder, when mixed here, does create a soft solid when it's mixed with this water. Okay, so there is a change to the initial powder. Powder, however, is also a solid, so there wasn't actually a change. Okay, it's just clumping together, if you will. And in this case, the vinegar test, when mixing with the powder, a gas is formed. So you've got a liquid and a solid creating a gas. So you have an actual change. But we are seeing some students who aren't understanding that a powder is a solid and the liquid, so you have a solid and a liquid creating a clumped together solid. So we are seeing students who are having a bit of a misconception or a misunderstanding about this, and they are seeing this word change. So there is some thought here about a new substance being formed. So there's some discussion to be had with your students as to whether or not was a new substance actually formed, or was it just a reshaping of an existing substance. So there is something to be said here. Students are not necessarily choosing something out in left field, but they are having a bit of a misconception, misunderstanding of the particular subject. This is not necessarily this is not a trick question. Some people would say this is a trick question. You're asking them something that's really close. It's very similar. This is actually along a progression of understanding. And so students are choosing an understanding that is very close to correct, and that's showing you that they're gaining knowledge. They're very close to what you want them to understand, but they're still not understanding that you're going from a solid and a liquid to a new substance, which is a gas. In this case, you've got a solid and a liquid that's just containing and creating a larger solid. So it's not creating a new substance, it's just a different shape of the same substance. So that's an important distinction, and one that is actually supposed to start happening in this grade level. So there is a difference there. And this does make that distinction. So it's allowing you to see what students are still kind of having that disconnect between knowing what's a new substance and what's just a change in the same substance. So that's important to know. In this next question, question number 3, one of the students argues that the design of all 3 tests in the investigation is flawed. Which 2 changes would most help ensure fairness in the investigation? You have A, using only 1 powder in each test, B, using the same type of liquid in all 3 tests, C, using the same amount of liquid and powder in all 3 tests, D, mixing an unknown liquid with each of the powders in each test, and E, adding the same amount of liquid to each powder in all 3 tests. Students who chose letter B. So a large number of students chose letter B, and it's somewhat indicated that they're keying in on that word same. They're seeing the word same, and they're keying in on fair test, and they're seeing same. And they're thinking fair test means all variables have to be the same. So this is an indicator that you have students who are using vocabulary cues to illustrate what they're looking for, as opposed to being able to look for the actual information and content that they should be looking for. So it's not the word same that they should be looking for. So if perhaps a teacher is saying you're always looking for the same, it's always got to be the same, it's got to be the same, it's got to be the same, then a student will cue into the word same. It's not about sameness, it's about fair test and making sure that your variables are kept constant. So that's very important. There's a difference between keeping your variables constant and keeping them same. So that's important. And then for 9A and B, we notice that the answer is C and D. C and D for 9A and B, but we also notice that 23 and 26% of students notice that some different things are going on here. So they're noticing that the weight will increase because matter changes as water turns to ice. And again, this is a significant misconception because a quarter of the student population feels as though water and ice are different, have different properties, that they aren't the same material. And that there wouldn't be conservation of mass between these 2 things. And so that's an important thing that you might want to revisit with your students. And then one more. In question 8B, the answer is A. 61% of students knew that the answer was A, but those who didn't seem to know what the answer was. So those who didn't know that it was A were guessing between the final ones, and so did not know which were the correct responses. And so there seems to be a confusion on this fair test issue. And this is the second question on this assessment where students were confused about fair test. So what does all of this mean? Well, we've already talked about these specific issues, question 2, 3, 9A and B and 8B, and what were the specific issues that were going on there. And as a teacher or as a professional learning community, if you come together and have these kinds of discussions and talk about what these trends are and what students are choosing as the most most likely incorrect response, or what these ideas are, what students are getting tripped up on. Then you can come together for this summary of planning forward. So what are you going to do about it? So we know what they got wrong, so what? They just got it wrong. So we're going to move forward to the next chapter, and that's just the way it's going to be. Except that you're going to be teaching fair test in the next chapter or next unit, and you'll be dealing with fair tests in the following unit. And this idea of conservation of matter and energy is built into almost every unit that we teach consistently throughout science. And so it's not necessary for you to go back and reteach within the same context that you've had before, but you can consider the idea of doing some other things with students throughout the year. So here you are early in the year, you've come to this conclusion. You can think about things like continuing or offering opportunities to practice fair test preparation for some of the other chapters and units that you'll be teaching. There's a lot of times for exploration and explanation and revision of thoughts in this area as you continue year to year, let alone in 1 year of science. Reteaching and offering extra experiences with PS1-4. That seems to be a standard that could use a little bit of extra experience for students, and you can actually embed that in future coursework. It doesn't have to be something that you do extra just because we just took this test, so I'm going to reteach you this concept and then we're going to move on. You can build it into future coursework. There's plenty of opportunity for that. And then identifying and reinforcing conservation of matter models with every opportunity that is consistently and regularly appropriate throughout science throughout the year. So similar things are available through state summative assessments. Now, not as detailed of information is available. With state summative assessments, there's a single proficiency score that says that students are proficient or students are not proficient when it comes to 5th grade standards, 8th grade standards, or high school biology standards. It's a general measure of proficiency. Now, the good news is, unlike DCAS, which incorporated 3rd grade, 4th grade, and 5th grade, and then in middle school it was 6th through 8th grade, and then high school was more than 1 grade worth of standards. For the DESA assessment, 5th grade is the 5th grade standards, 8th grade is the 8th grade standards, and high school biology are the biology standards. But the score literally means that a student is or is not proficient in 5th grade, is or is not proficient in 8th grade, and is or is not proficient in high school biology. And there are 4 levels of proficiency. So a level 1 means that the student is well below standard. That means that students are performing, they are able to do some things, but they're not able to do it at the level that's expected from the next generation science standards. A level 2 is below standard. Again, students are able to do some of the things that are expected, but they aren't able to do it at the level that the standards actually put forward. Level 3 is at standard. Level 3 means the student is doing exactly what the standards say that the student should be able to do. So if they are at a level 3 and you read the next generation science standards, students are doing the things that are there. If a student is performing at level 4, it means that they're performing beyond the standard. That means that they are actually doing some things that the standards ask at an above grade level approach. So they're able to do it with less scaffolding, more independence, and to a degree that incorporates more data analysis and evaluation. So for instance, for this particular student summative report, a student at a level 3 can complete tasks that focus their attention, so brings their attention toward using cross-cutting concepts to define a system and identify cause and effect relationships and patterns, that provide an opportunity for using scientific practices such as analyzing data, gathering information, communicating information, developing models, or constructing explanations, and applying foundational disciplinary core ideas to make sense of phenomena relating to the structure and properties of matter, ecosystems, and Earth systems, and stars and the solar system. At the policy or systemic level, differences between what students are doing has to do mainly with the amount of instruction or scaffolding a student needs to complete a response or cluster of items and the complexity of the concepts involved in the questions that a student is able to respond to. Note that at a level 1, a student is given specific instructions to define a familiar, simple system and to identify simple patterns using simple data. Conversely, at a level 3, a student can complete tasks that focus their attention toward using concepts to define a system, identify patterns, and analyze data. A student who's gone beyond standard doesn't need direction or scaffolding and can consistently use concepts to define novel systems to identify patterns and analyze and evaluate and use data to develop explanations and arguments to make sense of phenomena. When you're determining how to use data from state assessments to make curricular or instructional decisions, it may be most useful to look at the population trends in a given school or a district or within the system in which you intend to make decisions. So if you're looking at some state summative reports and you're looking at your specific district, in something like this. In this district, about 50% of students are at a level 3 or above. This means that at least 50% of students are achieving the standards or even doing more than what the standards are asking. So what does that mean? These are a lot of words, but it generally means that the students can complete tasks that focus their attention toward using the cross-cutting concepts, the practices, and the disciplinary core ideas to make sense of phenomena that have to do with the specific units of instruction that the students had anything to do with during that year of instruction. It also means that for each standard in that year, this is an example of 5th grade, that for each standard, a teacher can look to the achievement level descriptors that are found at this link right here, and they'll be able to identify the description of how a student is performing for each standard at that grade level. So let's take a look at something like that. So 50% of students were doing well. They were at a level 3 or 4. So for this particular standard, this performance expectation itself in 5th grade, conduct an investigation to determine whether the mixing of 2 or more substances results in a new substance. We've discussed this one. This is that chemical, chemical chemical reaction, thank you, the chemical reaction standard. A student who is meeting or above the standard can plan an investigation to determine whether the mixing of the 2 substances results in a new substance. That is the standard. That's what the standard says they can do. You'll notice that it's pretty much the exact same thing. A student at a level 4 can evaluate or revise an investigation to determine whether or not the mixing of 2 or more substances results in a new substance. So see, not only can they come up with an investigation, but they can look at an existing investigation and they can make it better. Or they can determine what's wrong with or how to improve an existing investigation. A student at a level 2, a student who's performing at a level 2, is able to use data from an investigation to determine whether or not a new substance was formed. Okay, so they aren't planning an investigation. They aren't looking at data and determining what investigation was done. They aren't figuring out what the fair test was for that investigation. They're just looking at the results of an investigation and determining whether or not a new substance was formed or not. And a student at a level 1 is able to regularly identify the order of steps for a simple investigation that would tell you whether or not a new substance would be formed. Okay, so think about a student who, they might be able to do all 4 of these things, but can regularly do number 4. or can regularly do number 3 versus a student who is struggling to get past level 1. Okay, these are the differences between a student performing at a level 1 versus a level 3. All right, so from discussions regarding broad-based lessons and activities with student expectations and regular classroom practice can be determined to see if there are any changes in instruction that are appropriate for future years. So basically, if you're looking at population reports and you're seeing that large numbers of students are performing maybe at a level 2, and then you come and you look at your standards and you start looking at patterns and what an achievement level 2 is. And then you look at your curriculum or your instruction and you say, well, yeah, that's what we do regularly in our instruction. We don't ever ask them to do an achievement level 3 or a level 4. Then having discussions about ensuring that you do have students do a level 3 and a level 4 in the classroom allows them to practice and get there, because a level 3 is the expectation of the standard, and that is the claim that the assessment is making, and those are the data points that are being collected to say that a student is proficient. So you want to make sure, again, that your instruction and your curriculum are aligned with those achievement level descriptors, which are the performance expectations at a level 3. So the ALDs at a level 3 mirror the performance expectations or the standards for the next generation science standards. Okay. So thank you so much for joining us for this complete set of webinars for the Balanced Assessment System regarding Delaware Science. We hope that these sessions have been useful for you as you aim to build your own systems for success in your districts and schools. If there's anything that we can do to help you be successful, please give us a call. We'd be glad to help you in any way that we can. Take care.